So we get into some not fun stuff, inverse functions. I'm going to go through this fairly quickly. The gist of the lesson is taking the derivative of inverse functions, and I'm going to show you two different ways to do it. One of them will appeal to the memorizers in the group, because it's just a formula that, I shouldn't say just, it's a formula that you can plug and chug into. It doesn't make a lot of sense to me, but that's okay if that's what you want to use. I'll show you a different technique, which in my brain works a little bit better, but again, I don't care what you do, as long as you can get to where we need to get to. Okay, so, first of all, we want to verify that functions are inverses of each other. You know about that from Algebra 2 probably, if not then, pre-calc, and in fact, I think we've talked a little bit about that. If you make a composite function of the two functions, if it equals x, then they're inverses of each other. We're going to determine whether the function has an inverse function. We've talked about that already. What tests that? Say it loud, say it proud. Horizontal line test, right? Vertical line test tests whether or not a function, or whether or not an equation is a function. The horizontal line test tests whether or not a function's inverse is also a function. And again, that's kind of a nitpicky distinction that we make in here. Probably in advanced algebra and pre-calc even, you talked about functions having inverses, but you didn't really talk about whether or not the inverse is a function. Okay, we talked about that when you look at the sideways parabola versus the square root and all that other fun stuff. And then the gist of it is we're going to talk about the inverse of a derivative of an inverse function. And then you should be helped.
Why is butter on it?
Why what?
Why is there butter?
It's not, it's cheese.
Oh, okay.
Swiss cheese.
I don't know.
Yeah. And really oil shouldn't be up there either, that little, I assume that's olive oil in that little container, but
If it's water.
if it's water, you probably shouldn't drink it because it's yellow.
Where?
In the, on the lower right-hand corner.
Oh, I thought you were talking about the big bottle in the middle.
No, I think that's milk. Which really, milk isn't that healthy either.
It doesn't look
Unless
like
it's
Maybe I should pick a better picture.
I think it.
That's not that bad.
Or just stop thinking about it.
Yeah, why we stop thinking about it? Let's move on. That's salmon, no, salmon's good for you. Omega-3s and all that stuff. Okay, so you don't have to write this down because it's in the slideshow. You got the slideshow. There's no fancy way to explain this other than these are one of the few instances where you've got to just know the functions and plug and chug. And yes, you are going to have to know these. I will tell you, however, that there is a system to them, and I'll let you figure it out. But you don't have to be a rocket scientist to see how it works. Have you seen it already? You should really only have to know 3 of them. And it's similar to when we talked about the derivative of the trig functions. You really only need to know the derivative of sine, tangent, and secant because the co-functions have a pattern. You'll see the pattern here. It's identical, you just stick a minus sign in front of it. Okay? And you'll get to practice with that as you work through some problems. Okay? In the essence of saving time, I'm not going to do this problem because it is purely a quotient rule wrapped up with an inverse trig function. So you can see that if I go back to this slide, I know what the inverse derivative of the inverse of sine is. It's 1 over the square root of x, square root of 1 minus x squared. So I would do a quotient rule with this, or raise it to the -1 power, because again we've done chain rules, so you can do a chain rule or a quotient rule. I want to get to the more exciting stuff, and that is inverse functions. Okay, we've done this already, so I'll go through it quickly. You create a composite function with a function and its inverse, and if that value equals x for both of them, then they are inverses of each other. Think about something like x squared and the square root of x. You put x squared into the square root of x, you get x. You put the square root of x into x squared, you get x. Yeah, they're inverse functions of each other. Okay. The other thing is number 1, remembering that the domain is the domain of the function is the range of the inverse. The range of the function is the domain of the inverse. So when we were finding domains and ranges, I suggested that you forget about the range and find the inverse, and then find the domain of the inverse, which is always easier to do. This is really what I wanted to focus on for today's lesson. The method that I use is based on a simple concept, and that concept says if you graph a function and you graph its inverse, they're reflections of each other over the line y equals x, which, by the way, is that 45-degree angle with a slope of 1. I think I talked about that in the past. I don't know. If I didn't, here it is. Okay. The green function, I lied. The blue function is f. Its inverse is the green, and they're reflections of each other. If I fold that board along the line y equals x, they match up perfectly. So that we've talked about. What we haven't talked about is the two lines, L1 and L2. If I take the tangent line to any point on the original function, which we're calling L2 in that picture, it has a relationship to the line L1, which is the tangent line to the inverse. Are you with me so far? In order to use my method, you need to remember one thing, and that is those tangent lines have reciprocal slopes. And I'll go through this a little bit more. They're not opposite reciprocals, they're not flopposites, they're not perpendicular, they just have reciprocal slopes. Okay? The puzzle pieces will start to fit together as you watch me go through an example. So if I was asking you, what is the slope of the tangent line to the inverse of f at some point, I'm never going to do that. I'm never going to calculate directly the slope of this line. What I'm going to do is find the slope of the line to the original function and then flip it over to get an answer. So in other words, if this line has a slope of 4, I know this right away because I just flip it over, 1/4, done. Okay? For my brain, that works better. I like to work with the original function. That way I don't have to putz around with finding inverses and taking the derivative and doing all that fun stuff. However, one last point I'll notice, or I'll point out to you, what happens when you reflect a point over the line y equals x? The x and the y coordinates change. If this point is 2, 3, that point's going to be 3, 2. I know your head's about ready to explode, but stay with me here. Okay. So it'll make sense when you go through the example. Initially, I'm going to show you what the example looks like if you use the formula. Okay, so the formula is that guy right there. Okay. If I want the derivative of the inverse to f at x, it's the reciprocal of the derivative of f at the inverse. So that doesn't even make any sense to me. As it says, I'm not a fan of this one. It's a, what's that?
Not as fan of this one.
Not as fan of this one. Obviously, my English is not as strong as, or my typing skills suck. How would I not notice that? Not as fan of this one. That's such bad English. Not as, I can't even BS my way through that. It's just bad. Okay, let's move on, shall we? Thanks for pointing that out. I'm going to do this my method. Okay, so I have a cubic. And I want to know what is the slope of the tangent line at 3. This. So I need to take this through to a couple things. So if I go to the original function, if x is 3, I could figure out what y is, yes? But am I at x equals 3 for the original function? No, that's my y value. Because that has to do with the inverse function. So remember, they switch. So I find, using my method, there is one snafu. And that is finding the points that you're dealing with. Okay, so let's start with this. If I'm looking for x equals 3 on the inverse, that's the same thing as when y equals 3 on the original function. And that's an important point, so let me give it a second to sink in, and I'll answer some questions before I move on. Does this statement make sense? F of x equals 3. Do you understand where I got this? Yeah, everybody's good there? If you need a graphical representation, we can go back to this picture. I know that that point is 3. I don't want that point, I want that point. So the x value of this point switches to the y value of the other point. They already switch it, so it's 3 and 3 there. Okay? So I know that already. Where did this x come from? Well, I set that function equal to 3 and solved. Trust me on this one, it equals 2. That's not what we want to get bogged down in. Solving a cubic is not necessarily very easy. You're going to have to trust me. That's the key to the problem, because what I'm really going to do is I'm going to find f prime of 2. F prime of 2 is the slope of the tangent line to the original function when x equals 2. That's going to be able to tell me the slope of the tangent line of the inverse function when x equals 3, because I know that those 2 points are the reflections of each other. Yes or no? Kind of. So-so. Okay? Do you understand? Again, you have to trust me on where the x equals 2 is, because I'm not going to solve this. But what I did in order to get that was I said 2 is equal to 1/4 x cubed plus x minus 1. And I solved that. How did I solve that? I actually cheated and used my calculator. Okay, to be honest. Full disclosure. Oh, I lied. It's not 2. It's 3.
Okay.
There we go. Sorry. And that gives me x equals 2. That means the point on the original graph is 2, 3. The point on the inverse is 3, 2. That's going to be the biggest part that you're going to struggle with, is getting that relationship of the 2 points. Once I get that, the rest is pretty straightforward. Because now all I need to do, if I deal with this original point, is I need to find f prime of 2. Which is easy, yes? 3/4 x squared plus 1. That's the original way. Hold on. Let me get back to my... I'm skipping ahead. Hold on. I'm getting to my point. Here we go. Okay, so this is what I want to do. Here's my graph. There's my line y equals x. There's the original function. So I'll have some inverse that looks like... Oh, I don't even know if I can do this. It's all right. So this is the original function. This is f of x. This is f inverse of x. One point is 2, 3. It's up here. Change to red. Stay with red there. And its reflected point should be 3, 2. I missed a little bit. Should be down. Okay, so sorry. There we go. That's better. So I'm going to find the slope of the tangent line in red. And then I'm just going to flip it over. Okay. Oh, I thought I had it there. That's why I clicked. F prime of 2 is 3/4 x squared plus 1, which f of 2 would be 4 is 3 plus 1 is 4. That's the slope of this tangent line. How do I get the other one? I just take it and flip it over. Oops, that should be a 3. Is reciprocal. Again, not opposite reciprocal, but just reciprocal. All right, where did I lose you? Okay, so that means one of two things. Either I didn't and I'm a really good teacher, or you're so confused you don't even know what to ask. Right?
So you didn't lose me, but like I kind of just look a little confused on like this because f of x equals 3 when x equals 2, you know that f negative 1 3 equals 2.
You trailed off there at the end. I'm sorry, what?
F negative 1 of 3, f inverse f of 3 equals 2. Like, because like Oh, okay, never mind.
All this business is doing in red there is establishing what the point
Oh, okay.
and the reflected point are for the inverse versus the original. So 2, 3 is on the original function. We want the slope of the tangent line at 3, 2 on the inverse. So I'm not going to work with the 3, 2 because the inverse scares me. I'm going to work with the original function.
Okay, I was just confused with like how I forgot that f of x kind of means it means y, and I was just
Yeah.
like getting confused
Yeah, yeah,
with
yeah.
like
That's the other thing to remember is that f of x, and I guess I should have reiterated that remember f of x equals y.
okay.
Other questions? What's the matter? Are you cold? You're just laying your arm on the windowsill? Because that's normal? Are you okay?
I wanted to see if it was more.
It is? Yeah.
That was it.
Okay, cool. Other questions? All right. The good thing is, this isn't a major topic. The bad thing is, it's ugly. And that's why I don't like this at all, because it confuses the heck out of me. And for me, with my geometric background and my basically strong Algebra 1 skills, and being a visual learner, the graphical part of it makes more sense. Okay. Now, I skipped over it, but if you're interested, if you want to use the other method, it's right there for you to look at. You have it in the slideshow, you can go and look at that and see how it works. Okay. But it still requires doing the things that I've already done. Notice that f inverse of 3 is in that function. So I have to figure out what f inverse of 3 is. I still have to do the work to figure out that it's 2. Then I have to do f prime of 2, which I also did, and you get the same results. You also have to take the derivative. So there's no shortcuts either way. You're still doing the same things. It's just a different approach to the problem. One, to me, is more graphical. The other is more memorization, plug and chug. It's entirely up to how your brain works. Okay? Good? All right, so the plan is then, we haven't talked about day 18 at all. That's okay. Obviously, you have day 19 tonight. On Friday, we're going to do Friday as like a damage control day. So we'll get caught up on all the things. I'm sure that some of you have a bunch of questions about day 18. I guarantee you'll have questions about day 19. But I will try to not have a new lesson on Friday, and we can just play catch up on some of these things. Okay, good? Questions? Excellent. Let me stop the recording here.